So welcome everybody. Good afternoon. Thank you for joining us for this, our 9th out of 10 webinars that we're doing around the course collections, course enhancements initiative that you see on the page in front of you. This is the organic chemistry group, and I will turn it over to Dr. Rachel Brooks to kick it off.
Thank you so much. So welcome everyone. We are delighted that you are joining us, and we're very excited to share with you what we've been working on over the past 5 weeks for the development of the Organic Chemistry 1 course collection. So I just want to show you, you are going to receive a link in several locations, one of which you will receive in the chat, to the landing page for the UNC System Digital Course Enhancements Initiative, where you can access all of the courses, all of the course collections that have been created. And so we are going to take a peek at the Organic Chemistry 1 Teams page. And I just want to walk you through really quickly what you will find on this page. So here you will see an overview of the contents of the page, our design process, the module content, as well as how you can enhance your course. So I would like to highlight, first and foremost, our amazing team. We have had a wonderful opportunity when you're working with a group of persons in 5 weeks to develop a massive amount of content. It really can go either way. And so we're very fortunate to have a wonderful team of highly qualified and just very collegial colleagues who have dedicated their time and energy day and night over the past 5 weeks to help bring this resource to you. The team was led by our instructional design team from North Carolina Central University, my colleague, Dr. Jwaibi, who will be speaking with you in just a bit, as well as our amazing team librarian, Will Cross from NC State University Libraries, and our system liaison, John Fauci. We will talk about the process that we utilized for managing this project, as well we're referring to as our prototype-based process. When you navigate to this page, you will find 2 videos that explain both of these processes in more detail for those of you who are interested in knowing more about that back-end piece. And then you will also be able to access our module content by selecting Explore the Modules. You will first see the 5 SLOs that were created for this course, and we'll talk about how that was done collaboratively, as well as links to each of the 11 modules that had been selected to be included in this course collection. Under the Enhance Your Course section, there's information regarding how you can utilize the information that you find in this course collection to build within your learning management system, as well as strategies for communicating with your learners, incorporating the different instructional materials, tips for promoting interaction and engagement, how you can assess your learners online, as well as considerations for maintaining universal design in your courses. And then finally, we include a location on the page where if you select your institution's icon, you will be directed to various offices for faculty professional development, e-learning, centers for teaching and excellence, to receive assistance from your instructional design and faculty development support teams in utilizing the resources that you have found in this content collection. So the way in which we went about our approach to developing, we did have weekly meetings. We met every Thursday with a very targeted agenda. The very first meeting's task was developing the SLOs, and so we compared what are those expectations for learners successfully completing Organic Chemistry 1 across the system. And so we were able to collaboratively come up with the SLOs that you saw on the website, as well as identified potential module themes that eventually became the topics for each of the modules. At the end of each meeting, we identified the next steps, what our goals were for our team, as well as what our individual faculty experts had the responsibility of fulfilling, and how their instructional design support team was there to assist them. We created a prototype module as our first module and collaboratively developed that. And in doing so, we reminded each other of the SLOs for the course that were decided upon by the group, as well as provided individuals opportunities to suggest what the module level objectives should be. We then democratically voted on those MLOs, And together we created the first module. So here's an example of what you will find in each of the modules, the module mapping matrix, which highlights not only the SLOs of the course, but the objectives for that particular module, as well as the assessments, learning activities, the related SLOs, module level objectives, as well as any instructional materials and technology utilized in that particular module. After we developed that, our faculty experts created these using these transparent sheets that are actually guides now for you in the modules that explains what are the objectives of each of the learning assets. So the learning activities or the assessments, what are the objectives, what are the purpose and description of them, as in addition to some guiding questions to help flesh that out. There are also step-by-step instructions for students, and assessment criteria or evaluation criteria, and then finally the various materials and technology utilized for that particular learning asset. So after the development of that first module, we kind of built it out in the learning management system just for the faculty to see what this could look like. So here's an example in NCCU's Blackboard LMS. And so what happened after that is we went about developing the remaining 10 modules, and we focused on 5 modules at a time. We spent 2 weeks on each of those 5 modules. And so each faculty expert was responsible for a specific module, but each person was able to suggest and recommend MLOs for the 5 modules that were being addressed that particular 2-week period. Whoever was the faculty lead, however, for that module then identified what would be the MLOs for that particular module. And so as you see, this is how we went about developing the remaining modules for the course, for which you will find in our course website, as was shared earlier. So now Dr. Joibe is going to highlight this prototype-based process and share with you how we ended up creating the content that you will find.
Thank you, Dr. Brooks. Good afternoon, everyone. My name is Zachariah Joibe, and I am a senior instructional designer at North Carolina Central University. So when my colleague, Dr. Brooks, and I sat down, virtually of course, to discuss how we can approach this project in such short time without compromising its quality, we decided to use backward design as our course design approach. We decided to implement a prototype-based course development process, and we utilized QM standards as our quality criteria. So why backward design? We used it simply because it promotes purposeful learning and ensures constructive alignment. That means when we identified and constructed our learning objectives first, we were able to develop appropriate assessments, curate effective instructional materials, design meaningful learning activities, and also incorporate effective instructional technologies. And this has pushed us to emphasize quality over quantity. This means that every instructional material, every learning activity, every lab, and every assessment has an instructional function. And to ensure meaningful students' content engagement, our team made sure to implement backward design at the micro level as well. In other words, the development of every learning asset, not just the course as a whole, started with constructing measurable, specific, and clear learning objectives. As you can see, the prototype-based development process we have implemented consists of 4 main phases. In the first phase, our team identified and created student learning outcomes. We were able to list the potential themes or topics that would be our learning modules. Then we collaboratively created module level objectives for module 1, which was our prototype. In the second and third phases, our subject matter experts collaboratively developed a prototype. They created assessment, selected the instructional materials, developed the learning activities, and chose the instructional technologies as well as the lab component. And then the team discussed the prototype and agreed on its structure as well as its pedagogical sequencing. After that, the course mapping matrix was utilized to make sure that all the course components are well aligned. In the last stage, that's where our faculty members selected the modules or the topics they wanted to work on, and they started replicating the structure of the prototype module. Once all the modules were completed, we conducted a review of all the modules and faculty made modifications if needed. So why prototype-based process? Our use of prototype-based process was based on two main rationales. First, our reliance on it was not only to expedite course development, but also to offer just-in-time training and practice opportunities for our subject matter experts. We thought, and we were wrong, that some of our SMEs might not be familiar with online course development process and the implementation of some design concepts. However, we were very fortunate to having worked with faculty members who are not only experts in their subject matter, but also andragogically adept. As you might have already noticed from the sheet in front of you right now, the whole course development process was scaffolded to help our faculty members in this endeavor via including templates, samples, and resources, as Dr. Brooks showed earlier. We were also engaged in one-on-one and group consultations, and we provided continuous feedback on each learning object developed by our faculty members. And what I meant here by we is that all the team members, not just the instructional designers, but everybody and all of us and the faculty members were supporting each other and providing each other feedback. And honestly, it's been a great pleasure to having collaborated with such a fantastic team. We think that our collaboration hopefully will not end just because we are done with this project, and we believe that we might have developed a learning community. So our second rationale for implementing prototype-based process was that by creating a prototype at an early stage of course development, we were able to identify and rectify any potential design deficiencies and learning gaps early. And that helps us make the process to be a little bit more efficient and effective. We believe that if we didn't follow, or if we did follow the conventional course development process, the possibility to end up with drastically different modules would be very high. And that would make it a little bit difficult for our team to review and modify everything in a short time.
Thank you so much, Dr. Jouaibi. So now we are going to have Will Cross, our team librarian, to share a little bit of background about what you see here, our metadata sheet, and how we have collected and categorized and made available to you a system of identifying the various open educational resources throughout this course collection.
Great, thanks so much, Rachel. So hi, I'm Will. I'm a lawyer and a librarian on the team. And something I bet not many people expected when they began this project was a crash course in copyright and licensing. But the question of how we can use, reuse, remix, and reliably point to resources became pretty important pretty quickly. So for those reasons, we began with a foundation, as Rachel said, of openly licensed resources, what are often called OER, open educational resources. And these are anything from textbooks and videos to worksheets or any number of other things that are free for the system, for faculty and for students. So that's one reason OER was a good fit here. But more than that, because they have that open license, they're also reliable and editable. So they could be customized as we develop the initial resources, and so that downstream users can also tailor and localize the materials we have here to the various teaching styles and the diverse campus contexts that we hope will be using these resources. As you can see as you go through this, we've also included a smattering of resources that are free on the web but aren't openly licensed. So the final product, we have a mix of free and open, and we've done our best to clearly label each of these. This is a CC BY license. This is an all rights reserved resource, etc. Another thing that we did in organic, which I think is really useful, is we identified sort of a set of core resources that appeared across every single module. This textbook chapter, or this set of videos has a great video for every section. We pulled those out separately, and then we said in each individual module, there's a further set of sort of module specific resources. So if you say, I want to lift up this course and use it whole cloth, you can start at that first section and you'll find good things everywhere. If you said, I just want to pull module 4 into my existing course, you can find the right resources and the right modules as well. So I could nerd out about this stuff forever, but I think that's most of what I wanted to say about the open educational resources. So I'll turn it over and we can continue our discussion.
Thank you so much, Will. So now we are going to have our first faculty expert, Dr. Tanya Malloy, who is also our faculty lead from North Carolina Agricultural and Technical State University, who will be sharing with us a learning asset developed in Module 1, Remembering General Chemistry, Electronic Structure and Bonding.
Okay, thank you, Rachel. Good afternoon, everyone. So today we're going to begin by examining the learning activity from our developmental module. So this module is a crash course in a review of general chemistry. For this module, we selected 5 different module learning objectives, one of which was drawing resonance structures. So what you see here is the transparent sheet for this specific learning activity, which covers drawing and evaluating different resonance structures. At the beginning, we state clearly the module learning objective, which is MLO number 5, and then we explicitly state what the students are going to be or should be able to do after completing this learning activity. For each of these transparent assessment sheets, you'll notice that we'll have the description and the purpose. So to help bring to the students the importance of learning this specific concept and how it would benefit them as they continue on through this course or other courses in their curriculum. So next we're going to move into the step-by-step directions for this specific learning activity. The students began with watching a video, which is an introduction for resonance structures, to set the stage for what they're going to be expected to know how to do. The students have seen resonance structures in general chemistry, but now we're going to pay close attention to drawing resonance structures for organic compounds. This specific learning activity has the students complete 3 different tasks. For each of the tasks, the students will explore the information in one of 2 ways or both. So they can either view a website to read and take notes about the information. In addition to that, or in alternative to that, they can watch a video which explains it to them, walks them through different problem-solving strategies. At the end of each task, the students have the opportunity to practice what they just learned. The first task was drawing curved arrows and resonance structures. So we have an activity where the students can practice that skill. So we go back by introducing or reintroducing what the students saw, reminding them of some of the rules that they need to pay close attention to, give them a few examples, and then they actually complete problems on their own. So this one asks the students to draw the result of the arrow. So using the curved arrows, what the result of that will look like. And then the second page of this activity gives the students 2 different resonance structures and now asks them to show the arrows. So 2 different ways to target the same concept. The second task, which we have here, are key arrow patterns in drawing resonance structures. So again, the students can review a document for the patterns that they should look for. So there were 5 main patterns that we asked the students to focus on. We also listed the rules that they need to keep in mind to draw valid resonance structures, and then later on also evaluate the importance or stability of a group of resonance structures. After the student reviewed the activity or the document in the video, they then complete another worksheet. So now the students are given a starting place. They're asked to draw a specific number of resonance structures, and then they're also asked to find the pattern, one of the 5 main patterns, which one would apply to drawing the resonance structures for each of these shown here. So the third task the students were asked to complete was now a comprehensive review. So they were given a starting point. They were asked to draw different resonance structures and then use what they learned to evaluate the importance of each one. So finding out or labeling major and minor resonance contributors. And for this activity, we end with some interactive sites that the students can go to so they can build Lewis structures online if they need a review of how to do that from general chemistry. And we also have different worked examples so the students can see the rationale behind these problems.
Thank you so much, Dr. Malloy. So now we have Dr. Kirsten Dakin from North Carolina State University, who is going to share with us a learning asset from Module 3, Acids and Bases, Central to Understanding Organic Chemistry.
All right, good afternoon, everyone. So before I talk about this learning activity and the sheet corresponding to it, I first wanted to kind of situate everyone with where this lies within this module. So as we all know, acid-base chemistry is really, really important in the understanding of reactions later on, but also in terms of the mechanisms that are related to these reactions. So in this module, what I did was I took each module learning objective and I created one learning activity related to them. So for this module learning objective, this is the one that's developing number 4 of 5 for this module. This is really building upon the previously practiced skills of this module. So for this learning activity, we're looking at predicting the outcomes of acid-base reactions. So in order to get to this, there are 3 other skills that they've really developed. And we see that one of them is directly related to this, right? Predict the relative acidity or basicity of organic molecules based off their structures. And once we can do that, we can actually understand the outcome of these acid-base reactions. So this learning activity is really meant to take those 3 previously learned skills, make it integrated into this one learning activity so that they can take all of these 4 module learning objectives and apply it to the last one of this module. So first, what students would have to do for this learning activity is to complete the learning activities on 1, identifying types of acids and bases. So this is where they will learn how to differentiate between your Arrhenius or your Bronsted-Lowry or your Lewis acids and bases. So that's the first that they have to accomplish. Then identifying acid-base conjugate pairs, which we know is related to Bronsted-Lowry acids and bases, but that is going to be important in the 3rd module learning objective, which is predicting the relative acidity and basicity of organic molecules. So after completing those 3 learning activities related to those 3 learning objectives, we are now here at this learning activity. And so I then direct them to 2 different resources. The first is how to determine the equilibrium position in acid-base reactions. And the next one is reading about reversible and irreversible acid-base reactions. Now, at this point, I kind of want to pause and talk about my intentionality of these 2 steps. We know that depending on the type of book that you're using, your book may hit on reversibility or irreversibility a little bit differently. So a lot of the major books, right, your Carey, your Brown, your Klein, don't really talk a lot about irreversibility, but a lot of your other online resources may talk about irreversibility. So I made a note of this also in the instructor resources so that depending on your book and depending on how you're presenting this to your students, you have a little bit of understanding of, you know, whether you need to develop one or leave one of these steps out. So after completing those steps, then the students are led to the learning activity sheet, which is predicting the outcomes of these acid-base reactions. And so I can bring that up here quickly, where we'll see that the first problem in this learning activity is focused on identifying of the 2 species given, which is the acid and which is going to be the base, and then determining the outcome of that reaction. Along with that, they are asked to show the arrow pushing mechanism of the product formation. So which one's the base, which one's the acid, what are the conjugate acid and conjugate base formed, and how are they formed? After doing that, in problem 2, they're asked to identify whether equilibrium will lie to the left or the right, or whether it's going to be towards the reactants of the products. So again, at this point, that might be, depending on how you talk about reversibility, you may need to adjust that one. But also in this learning activity, I did include one problem that really sets them up for understanding reactions later on with Lewis acids and bases. So identifying electrophiles and nucleophiles and the mechanisms that will be at play. So as you can see with this module, what I've really done is try to set them up for understanding reactivity and how that will apply to mechanisms later on in reactions.
Thank you, Dr. Dakin. So we now have Dr. Elizabeth Walters from the University of North Carolina at Wilmington, who is going to show a learning object from Module 5, Isomers, the arrangement of atoms in space.
Sorry, everybody. Good afternoon. Thanks, Rachel. Now I'm on. I wanted to talk to you today about a dry lab activity that was developed as part of the isomers module. This is the last of 4 dry labs that could be incorporated into an isomers chapter. This one is specifically about enantiomers and diastereomers, the similarities and differences in physical properties as well as optical activity. Prior to getting to this point, in terms of the content of the module, there was learning activities with respect to constitutional and stereoisomers, and then taking stereoisomers and differentiating between enantiomers and diastereomers, as well as teaching the students and learning about RNS designation. There would be ideally a learning activity, which there is. It could be a lecture type activity on optical activity prior to the dry lab. And the use of this could be as a lab, it could be used by your lab coordinators, it could be used in lecture a lot, I guess, still depends on what we find as we get closer to the fall semester. So for this learning objective, it ties very well to our student learning objectives for the course, with structure and physical properties as well as stereochemistry. So there are some learning objectives that sort of pull in information from various learning activities students would have completed prior to this dry lab. And then as it's a lab, one of the things that I wanted to have the students practice is utilizing widely used and reputable web sources in order to look up desired chemical information. So the molecules I've chosen aren't particularly hard to find, but I would encourage our students to use proper citations and proper websites. Then students are asked simply just to complete a single activity worksheet and access PubChem in order to, or that's one source, but they could use others. And then a key is provided for instructors or lab TAs or lab coordinators in order to facilitate grading of that activity. Again, assessment would be 70% completion would be satisfactory, mastery would come at a 90% level. And then in terms of technology, it's simply a single worksheet with a key. If we take a look at the worksheet, like I said, the molecules aren't terribly challenging. Most students in textbooks include carbone when discussing optical activity. The information that they're given is simply one of the molecules, and they would have to draw the enantiomer, identifying which is the R and the S isomer. And then the activity continues with students using PubChem, or again, a reputable source, in order to pull information of the physical properties. And at this point, like I said, there are 3 labs that come before this, and one of the labs, or 2 of the labs, excuse me, do utilize thin layer chromatography information. So hopefully at this point, students would recognize that enantiomers would have similar physical properties, and this should be a quick activity for them to complete. But then they are asked to account for why that would be, bringing in previously learned information on intermolecular forces and structural aspects of polarity. In the second activity, or part of this activity, is to address racemic mixtures for carbone, as well as to ask students to discuss whether or not R or S stereochemical designations relates to the direction of rotation of light. The last part of this activity is to use a molecule with multiple chiral centers so that we can increase the number of stereoisomers students will consider. In this particular compound, they'll have both an enantiomer and diastereomers, and they're asked to draw an enantiomer, identify the relationship, comment on physical properties, similarities, and differences, and then draw a diastereomer, although those words aren't directly used, they're discussed in terms of related or unrelated optical activity. And that would be the end of this part of the optical activity worksheet, and then the next two learning activities after this within the module would address meso compounds, which could be tied in here, but in case your university doesn't cover that or it's overwhelming, this would be a good stopping point. And as mentioned, then there is a key provided with data from PubChem, so it should be an easily graded activity.
Thank you, Dr. Walters.
Thank you.
Up next, we have Dr. Marion Franks from North Carolina Agricultural and Technical State University, who share a learning asset from Module 6, Alkenes, Structure, Nomenclature, and Reactivity, Thermodynamics, and Kinetics.
Good afternoon, everybody. In terms of talking about alkenes, I want to start you off by just pointing out that the alkenes are one of the first few functional groups that a student would learn. In fact, it's probably after alkanes and then after alkyl halides, you have the alkenes. Their importance is that they're found in many industries, including the petroleum industry, pharmaceutical industry. They're found in various places where students would have interest. So as we move into this transparency sheet, which is going to be a guide for the student, the first thing that we learn is that the students learn the learning objectives. There are a few learning objectives that are given to the students that will show them what they will be learning. Mainly, they will be learning about the processes of dehydration and dehydrohalogenation throughout both of the activities that are in this particular activity sheet. As we go forward, as they continue on their pathway in this transparency, they'll also find other things that they'll be expected to learn, and they will know at the end, such as being able to predict the product of a dehydration reaction, predict the product of a dehydrohalogenation reaction, and they will learn how to tell what type of alcohols are being used. One of the interesting notes about this particular module, and we see this, I guess, in all of the modules, is that there is a lot of overlap that happens between modules. This particular module happens to overlap with the next module that can be covered by the instructor. This particular activity also overlaps with other activities that the students will be doing even after this particular activity. And that's somewhat intentional because we know that learning takes place when the students can enter into learning about content over and over and over again, almost in a spiral-like fashion. So as we go to the step-by-step directions, we've given direction to the students both by telling them to look in the materials and technology needed section to review some of the parts that they'll be learning, but also as they continue reading. One of the things that we know is that sometimes students will come to you and they'll tell you that I'm lost in the class. Well, if they're following the transparency sheet, they'll be able to click on different spots and actually be taken to websites and be taken to videos that can help them so that they won't be so lost. And even with that, we also introduce things like Zaitsev's rule, a quick cheat sheet for Zaitsev's rule right in the midst of the transparency sheet, so that it gives them a guide that they can always refer back to, even if they don't have internet access. And then after that, we have the assessment, and this is a suggested assessment to the instructor, suggesting a way that they can grade this, because there are two parts, but I wouldn't say that both parts are given equally. But what does turn out is that 70% to 89% is seen as being competent, and 90% shows mastery by the student for this particular module. So as we look at the actual activity, we're talking about the synthesis of alkenes, And in talking about the synthesis of alkenes, the first method in synthesizing alkenes is dehydration reaction. So what is given are dehydration conditions and an alcohol. From this, a student can learn how to use the alcohol and how to predict what product would come about, what products would come about from the dehydration reaction. Now, in most of these cases, there are several alkenes that are formed. And the second part to this particular question asks them to circle the most stable alkene that is formed. There are also rearrangement reactions that take place. And the student is expected to know that there will be a rearrangement that happens. In the second part of this.
I apologize. We don't have that up on the screen just yet.
Oh, I'm sorry.
That's all right. Thank you.
Is it there yet?
Yes, phenomenal. Thank you.
I'm so sorry. So once again, you have alcohols, and in this particular case, you have reaction conditions that are given. In most of these alcohols, you have the student being able to do a rearrangement reaction, or a student being able to form many products, and the question asks them not only to show all of the products, the product or products, but it also asks them to circle the most stable products, which goes back to Zaitsev's rule. In the second part of this particular question, or this particular activity, the students are given various reactions, and they are given two sets of reaction conditions. One set of reaction conditions leads to a Zaitsev product, that's part A. The other set of reaction products lead to a Hoffman product, that's B, and it uses a bulky base. And the student is expected to know which of these which of these conditions should be used to lead to the products. By doing this, it sets the table for the student to understand both mechanism and also to get them prepared for their next learning objective. Thank you.
Thank you, Dr. Franks. So we will now have Dr. Dan Kristen from the University of North Carolina at Greensboro, who is going to share content from Module 10, Radical Reactions and Polymerization.
Yeah, good afternoon, everyone. So as Rachel said, radical chemistry. And so in this course, we've actually included two chapters that allow some flexibility. So we have a chapter on radical chemistry that at UNCG is actually covered in the second semester, because our textbook, Bruce, covers that a little bit later in the textbook. But that could be different at your institution. And so this is included here just in case. We also have a chapter on spectroscopy in case your institution or UNCG covers that a little bit earlier. So what is the structure of this particular module? And so basically there's an assignment side and an assessment side. And so you have in the assignment side 4 potential assignments that you could choose, one based on reactions. And so these are formulated in the way that reactions are typically tested in a course. And so students could be given the starting materials and the reaction conditions, and they're asked to predict what the products are, including the correct stereochemistry. They could be given the starting materials and the products and be asked to provide the reaction conditions for the reaction. Or lastly, they could be given the reaction conditions and the product and asked to provide a potential starting material. And that is followed by a problem set, very short one actually. All the problem sets here are pretty short for this chapter, because they're in the radical chemistry chapter, there are only really 3 reactions, which I'll show in a moment. And the second problem set will be about mechanisms, and that will test the students on the 3 mechanisms. And those particular assignments are also mirrored in the assessment files that are present in the. Lastly, I've added 2 other assignments regarding polymers. And so the first one is about radical mediated polymerization reactions, and I will show you that in a moment. And the second one is actually a nylon 6,6 synthesis that could be used as a virtual lab. And so what else is included in this particular module? And so we have, of course, for all the assignments and the assessments, transparency sheets. For the assignments and assessments, we have keys, and also included are the ChemDraw files, so the source files if you want to manipulate those to write your own questions, or if you find a mistake by chance, which could happen, and then you could modify that. And as is typically the case for our development work here, we try to rely on OER resources. And so one of the best resources for organic chemistry lectures is at UC Irvine, where they actually have 2 lectures for an entire year of organic chemistry. There are 51 A, B, C sequence, so 2 of them. And they also have some advanced organic lectures if you're interested in those. I provide PDF extracts from the Chem Reader OER textbook on both radical chemistry and the little bit they have on polymers. Students can also be pointed towards resources from Khan Academy, Layout for Science, and Master Organic Chemistry. And so the way I typically envision this module to progress is that an instructor will give a lecture about radical chemistry that encompasses the material that students will be then solving assignments and also be assessed on. And so those could be done using face-to-face approaches, Zoom lectures, PowerPoint, or whatever else you can think of in today's environment. And then the intention is that the students will complete assignments 1 and 2 on reactions and mechanisms before getting to the polymers assignment. But once again, you can really choose anything in this module that you want to use. That's up to you. And for the 3 main reactions covered in both the reactions and the mechanisms assignment are the bromination of alkanes, the anti-Markovnikov addition of HBr to alkenes, and the allylic bromination reaction. And so polymers are, of course, hugely important in our lives. We wear them every day. We eat biopolymers of different kinds. They're used to construct our houses, cars, furniture, and so forth. And so they really are very useful things. And so the polymer sections are really sort of more optional assignments, but they should probably be included if you're teaching as part of an ACS certified program. And this also will introduce students to direct connections between organic chemistry that's a little bit more abstract in the course and in the real world, and will also provide them with some practice in using web-based resources. And so here's the transparency sheet for this particular assignment. As you can see, it only has 1 MLO, and that deals with really writing a reaction mechanism for a radical mediated polymerization reaction. And this relates to one of the course SLOs, namely number 4, about using reagents for functional group transformations and carbon-carbon bond forming reactions. And as I mentioned, this is really activity number 3 in this particular module, and is dependent on students first completing the prior 2 assignments on both reactions and mechanisms. The assessment is a typical 70-90 for approximate C and A grades. The web resources that are linked to this particular assignment, and so these are actually resources that students can look at to complete the assignment, as you will see in a moment. Get to the assignment. And so this is a short little 1.5-page assignment. It gives a very brief introduction to polymers. And so there's a number of different monomers shown, the polymers that can be obtained from that, the generic monomer structural unit, and also some of the applications of those polymers in real life. And then we get to the first and really only chemistry-related question in this particular assignment, and that is to provide a mechanism for the free radical polymerization of ethylene to make polyethylene. And so in the context of the reaction mechanisms, usually we develop sort of an idea of initiation, propagation, and termination steps. And so those can also be applied in the context of writing a mechanism for this reaction. And as you can see then, the next 4 questions are trying to relate what we learn in the lecture course to real-life chemistry. And so in particular, question number 4, what are the common uses of these polymers, and to use any of these polymers in your life, right? So early on, I asked students to go essentially look in their house to see what kind of plastics and polymers they have, and if they can find the recycling symbols, and then can figure out what kind of polymers they're using. And so obviously they'll learn pretty quickly that anything that pretty much stores food, if it's not a can, is probably made out of a polymer. And so that's all I have for today. Thank you.
Thank you, Dr. Kristen. So to wrap up, we have Dr. Malloy from NCA&T, again, who is going to share with us our last artifact from Module 9, which is on the reactions of alkynes, an introduction to multi-step synthesis.
For this specific module, we're going to focus on another learning activity. This is the second of 2 learning activities within this module, which focuses on the addition reactions to alkynes. So this module ideally will follow Module 8, which is the previous module, the addition reactions to alkenes, because a lot of the reactions that the students have seen in Module 8, they'll see again in Module 9 with the alkynes versus the alkenes. So a lot of the foundation for this module was built in Module 8, in terms of knowing Markovnikov's rule, examining the regioselectivity and stereoselectivity of the different reactions. At this point in the semester, as we all know, the students tend to get a little bit tired, so we try to make it exciting for them, just give them a practical application of where they can find alkynes in drug synthesis, and then kind of reinforcing that these modules at the end are going to help the students build their toolbox to help them be successful in organic synthesis and retrosynthesis as they continue in the organic chemistry series. For this specific module, the students will be asked to examine the alkyne addition reactions. In the previous learning activity, they will have learned how to synthesize alkynes from elimination reactions, and then also starting from an alkene. So we jump right into covering the addition reactions. The students begin with a big picture, so the types of reactions that will occur and the types of products that they'll see. In the second step, we move into separating the reactions individually. And as you see, the students have a site to refer to and also a video to watch to show them the mechanism for the reaction and the predicted products, along with stereochemistry and determining major or minor products if there are any. The students are also going to be provided with a document. It begins with a spider diagram showing them all of the different reactions, including the elimination reactions that lead to the formation of the alkyne. On the last page of this, we have broken down for the students if they'll be required to know the mechanism or not, and you can customize this if you require the students to know additional mechanisms. We also have the action listed so the students can make note cards if they would like to, which is one way that can help facilitate the learning of this information by the pattern recognition. And then we also have regiochemistry if that's important for the specific reaction. For the first learning activity worksheet within this module, the students will approach the reactions from 3 different angles for a holistic view. So in the first type of problem, the students are given the reactants and the reaction conditions and asked to predict the product. For the second set of problems, the students are given the starting material and the product, and then asked to provide the necessary reaction conditions. And then in section 3, the students are given the reaction conditions and the products and asked to work backwards to determine the starting alkyne. To end this module, just to bring it all, or to this learning activity to bring it all together, the students are given multi-step reactions, so incorporating many of the reactions they've seen previously. They're asked to produce all possible products and label the major product, and also use the curved arrows to show the flow of electrons for the mechanism.
Thank you so much, Dr. Malloy. So that concludes our demonstration of the content collection. I do want to emphasize yet again that this is just a representation of a variety of learning activities, assessments, and virtual lab activities that have been created for you carefully to align with the stated SLOs of this content collection. And keep in mind that this can be used as to supplement your course. You can use all of the modules, you can use just a few of the modules, and then you can use elements from the modules, but it was designed to help you seamlessly integrate a variety of additional instructional materials and activities to support what you are doing as you are teaching Organic Chemistry 1. So thank you for your time, and we look forward to receiving any questions from you as we are wrapping up. I'm gonna turn it over to Michelle.
Thanks so much, Rachel. I would love to take the time to entertain questions, but we have one more webinar going up at 4 o'clock. And so if people have questions, they should email us.
Absolutely. Please feel free to direct questions to me via email, and I will be glad to get that to the team and get them back to you.
Great job, ORGO team.
Thank you.
Thank you so very much. So impressed with the efforts of our UNC system faculty. Never had any doubts, but continue to be amazed at how much this group cares and contributes. Thank you so much.
brief request. There is a link to a feedback survey that I put up in the chat, and we really are hoping to get feedback that can help direct improvement in the project. So if you could follow that link and give us some feedback, we would be so grateful.
Yes, I forgot to do the webinar, the survey for the webinar. So yes, thank you very much, Karen. All right, we may have a module for Chemistry 2 in the future, but not yet. Thanks, everybody.